Here we have a relationship between Rocket Sega and we have the Earth. And we're going to observe the position vectors between the Earth and Rocket Sega in these two different time intervals. And we're going to check the velocity, given that we have the change in time from this first position of Rocket Sega in the second. So the main things we want to know is the velocity, the average velocity of Rocket Sega, and then secondly we want to know what is the change in position of the position vector of the Earth's gravitational force acting on Rocket Sega from position 1 of Sega and position 2 of Sega. So it's important for us to recall the change in time is the final time minus the initial time. Our change in position is our final position minus our initial position. And to find our unit vector, we need to divide the vector by the magnitude for each component. And our average velocity is going to be our change in position vector divided by our change in time. So for our first part, we want to find what is our average velocity for Rocket Sega. So we have our change in position, because we have our final position, we can subtract our initial position from that. Then we are given our change in time over this period between these 2 points. So simply respect the average velocity vector formula and then plug these values in, and we find that our average velocity for Rocket Sega is -4 times 10 to the 12th, -1.6 times 10 to the 13th, -1.6 times 10 to the 13th meters per second vector. And for part 2, we're asked to find the change in direction of the unit vector for the Rocket Sega to Earth. We see that our vector is pointing in this direction in the first position and in this direction in the second position. So in order to find our change in unit vector direction, we need to subtract our initial unit vector direction from our final unit vector direction. So to find these unit vectors, we simply need to divide the vectors by the magnitude of that vector. So here we have the vector of planet Earth minus the vector of the rocket at position 1. We took the magnitude of that value and we divided it by that magnitude. And we did the same thing for the second position. We have the unit vector for Earth minus the unit vector for Rocket Sega at the second position. And then we found that vector and we divided it by its magnitude here. And we find these values. For Rocket Sega in position 1 to Earth, we have this unit vector. And for Rocket Sega from the second position to Earth, we have this vector in the blue here. When we take the difference of these, we find the change in the unit vector direction from Rocket Sega to Earth to be -0.04, -0.677, -0.309. Thank you, sir.